Okay, so let's just admit it, we are swimming in data. It's everywhere, right? From the apps on our phones to massive scientific breakthroughs, we're just generating unbelievable amounts of information. But what do we do with it all? How do we make any sense of it? Well, that's the big question, and it's exactly what we're going to tackle today as we dive into statistical learning. At its heart, every single complex data set has this one fundamental puzzle. There's a true underlying pattern. That's the signal, but it's almost always buried in this sea of random, unpredictable stuff. That's the noise. The entire goal of statistical learning is to build the tools we need to tune into that signal and, just filter out the noise.
And believe it or not, this entire super powerful field can pretty much be boiled down to one simple, really elegant formula. It's the starting point for everything we're about to cover.
So let's get a proper definition down. Statistical learning isn't just one single method. It's more like a whole toolkit. And the goal of every single tool in that kit is to figure out the relationship, the connection between some things we know, our inputs, and a thing we really want to understand, our output. And here it is, the big idea. I know, it looks incredibly simple, but this little equation is the absolute bedrock of machine learning and modern statistics. All it says is that any output we care about, which we'll call y, is just some function of our inputs, x, plus a little bit of a random error, epsilon. And our whole job? It's to figure out what that mysterious function f really is.
Let's break this down. So y is our output. Think of something like product sales, or a stock price, or even a medical diagnosis. X is all our inputs, the predictors, so things like our ad budget, historical stock data, or a patient's vital signs. The real magic is an F. That's the systematic pattern that connects them. An epsilon? Well, that's just the random noise, the irreducible stuff we can never predict. Like a customer just having a weird day and not buying anything.
Okay, this picture is a perfect way to see what's going on. Let's imagine we're looking at someone's income based on their years of education. That smooth blue curve, that represents the perfect, true relationship. That's our F. But of course, real-world data is messy. The actual data points, the little black dots, they don't fall perfectly on that line. That vertical distance from each dot down to the curve, that's the noise. That's our epsilon. And here's the kicker. We only ever get to see the dots. Our whole job is to try and guess what the blue curve looks like. So this brings up a really important question. Once we have our data, why are we even bothering to estimate this hidden function f anyway? Well, it turns out there are two very different and very important reasons. Are we just trying to make a really, really accurate forecast? Or are we trying to deeply understand the relationship between our variables? Because your answer to that question completely changes the kind of model you're going to want to build.
See, for prediction, all we care about is accuracy. That's it. Our model can be a complete black box. If it correctly predicts y, we honestly don't really care how it works. But for inference, the goal is the exact opposite. It's all about understanding. We need to crack that box wide open because we want to learn the how and the why behind the relationship between x and y.
With inference, we're asking really specific questions. Things like, which of our ad campaigns actually lead to more sales? Or does spending more on TV ads have a positive effect, or maybe even a negative one? And is that relationship a simple, straight line where more money always equals more sales? Or is it something way more complicated? These are all questions about understanding, not just predicting a number. Okay, so we know we need to estimate F, but this leads us to what is probably the single biggest dilemma in all of statistical learning. Just how complex or how flexible should we make our model? This right here is such a classic trap. You can build an insanely flexible model, like this super wiggly line, that perfectly hits every single data point you have. It literally has zero error on the data you trained it on. But it hasn't actually learned the true signal. Not at all. Instead, it's just memorized all the random noise. We call this overfitting, and it's an absolute disaster when you try to make predictions on new data. And that brings us to a crucial point. You have to understand the difference between training error and test error. Training error just tells you how well your model fits the data you use to build it. An overfit model is going to have a beautiful, wonderfully low training error. But the real test, the only one that actually matters, is the test error. How does the model do on brand new data it's never seen before? That is the true gold standard of performance. So how do we find that sweet spot? The model that's flexible enough to find the signal, but not so flexible that it starts memorizing the noise. The answer lies in one of the most fundamental ideas in all of statistics, the bias-variance trade-off. All right, first up, let's talk about bias. Bias is basically the error you get because your model is too simple. Imagine trying to describe a big, complex, curvy relationship using just a straight line. Well, your model is going to be fundamentally biased. It's making assumptions that are just plain wrong, and because of that, it's going to miss the real pattern. Now, on the other side of that coin is variance. Variance asks, how much would your model change if you trained it on a slightly different set of data? A super flexible, wiggly model has really high variance. Even a tiny change in the data can make it swing around wildly because it's reacting to every little bit of random noise in that specific data set. It's unstable. And this graph, this is the whole story right here. Look what happens. As you make a model more flexible, its bias tends to go down. That's the blue line. But at the same time, its variance goes up. That's the orange line. The total test error, the red line, which is what we really care about, is a mix of both. And you see that perfect U-shape? The best model, the one with the lowest error, isn't on either extreme. It's right there in that sweet spot in the middle, perfectly balancing the trade-off. So the takeaway here is huge. You just can't have your cake and eat it too. It's impossible to have zero bias and zero variance. A great data scientist knows the goal isn't to get rid of one or the other. The real challenge is to find that beautiful sweet spot where their combined damage, their total error, is as small as it can possibly be. And this trade-off isn't some abstract theory. It is happening right now, under the hood of almost every smart system you use, from your streaming recommendations to complex financial models. So the next time you interact with one of them, just ask yourself, which way is this algorithm leaning? Is it favoring simplicity and stability, or is it going for flexibility to capture every tiny detail? The answer to that question reveals the core principle of its entire design.